everybody. As you can see, Professor Alexenko is not here. She's out of town. She should be back Monday. But I'm here. I'll be talking about DSMC, something you'll be kind of learning more formally later, as soon as this PowerPoint loads up. Sorry, almost there. All right. All right, let's hope this works. Can we go to the screen? All right, so we'll talk about kind of DSMC and some background there. So for sure, this lecture we'll try to get through the introduction to non-equilibrium flows, things you should have some introduction to, and talk about Boltzmann equation, distribution function, and we'll talk a bit about DSMC, and hopefully we get into a bit this time, but next time it'll be more in depth, showing you how to actually use SPARTA, which is a DSMC solver, and many of you will probably be using that for your projects. The first thing, kinetic theory of gases. This is probably some of what you studied. It connects to microscopic and.
You want to put that microphone on.
Sorry.
That way you don't have to hold it and it's a little more constant. Get that right, yeah. Thank you.
Yeah, here.
Let me try.
Sorry.
Well, looks like it got broken. Okay, there we go.
All right. So kinetic theory of gases connects microscopic to macroscopic worlds. So the microscopic are like specifically on the molecular level. Macroscopic are the overall properties you see, like pressure, number density, temperature, and velocity, and those are connected. So if you look, can you see the mouse fine? Yeah, so in this case, we just see like a regular molecule. It has a movement. So that's a translational energy mode as rotational and as vibrational. So that, right there goes to different energy modes that kind of relate to your translational. So those are your energy levels from the molecular level. But on the macroscopic, they relate to your translational temperature, rotational temperature, vibrational temperature. And if you get to really high energetic flows, you'll have these, electronic temperature. That would be excited. And then one thing that's important is the collisions, molecular collisions. They stimulate these internal exchanges. So when you have two molecules colliding, they're going to, some sort of energy exchange is going to go on. They're going to obviously change their velocity, things like that. You can imagine just any sort of collision, just like if it's happening in the macroscopic world. Same thing happens in the microscopic world. And one thing that makes sort of this flow regime, the rarefied or even free molecular flow regime, so unique is that when you don't have a lot of collisions, or in fact very few, which you get once you get to really high altitude flows, or really low pressures, your energies aren't necessarily balanced. So you get non-equilibrium conditions. And this is kind of key down to non-equilibrium collisions. You cannot neglect these molecular processes. So you really have to know what's going on for every molecule. And that's kind of where the continuum hypothesis, one of the ways in which the continuum hypothesis breaks down. So this is where you can't start using Navier-Stokes or your CFD codes, things like that. So just kind of previously said, we do really need to try to track every molecule. However, that's impossible. There are so many molecules. If you think of a system, even under atmospheric number density is about 10 to the 25. If you even go down way lower, let's say 10 to the 15, that's very low pressure. It's 10 orders of magnitude less than atmospheric pressure. But if your domain is a cubic meter, that's still 10 to the 15 particles. So that's too many to track computationally. So we need to try to find the probability of particles within a certain range of states. So that means it's going through these distribution functions, and that way you can sort of approximate, kind of guess, I think the probability of this molecule being located at this location, having this velocity, and this translational, vibrational, internal energy, or various internal energies, things like that. So for example, there's these distribution functions here. So if we have like different temperatures, and there's so we have velocity on the x-axis, and under different gas temperatures, we see that the probability of our molecules have certain velocities. So you see, like for example, for 200 degrees, most likely our velocity is here, 800 most likely it's there, and basically you just randomly sample from this distribution function. So with this sort of different ways we find the distribution functions of having our particle in a certain volume element in a certain location, certain coordinates, and with a certain speed or velocity. So now getting more into the direct simulation Monte Carlo method, or DSMC. Key thing, first principle we have to talk about is Knudsen number. I believe you talked about this already. That's a mean free path, which is the average distance your molecules travel before colliding with another molecule, divided by your length scale. And length scale is something typical to specific to your problem. And this characterizes your flow regime. DSMC is applicable for all Knudsen numbers. However, because you're tracking kind of every molecule, it's only makes sense computationally to use when your continuum solvers won't work, or if there's kind of some benefit to that. But so you see here this graph here. So kind of your Navier-Stokes, even Burnett equation. So this is all what your CFD covers, up to a bit over a Knudsen number of 0.1. Once you get above that, you can't use a continuum solver. So at that point, you have to, DSMC becomes a beneficial method. And there's some other Boltzmann solvers out there, but DSMC is kind of the most common one, and certainly one that we'll be talking about here, and one that you guys are certainly invited to use for your project. So DSMC is a stochastic or probabilistic approach to solve the Boltzmann equation for dilute gas flows. So first, dilute, that's an important part. That means that if I have a certain volume, it's not dominated by molecules. So the kind of volume ratio to my diameter ratio is very large. Mostly it's empty space. So here I have my Boltzmann equation. So I have a time-dependent factor, and then here this is sort of the movement portion, and I have binary collisions, or collision integral here. So free flight, pretty simple. It's just collisionless motion. Molecule is just moving at some velocity over a certain time step. And I have, my collision, and that's represented by that collision integral. And then once this collision happens, obviously the velocities change, your internal energies are exchanged, things like that. And key, obviously you have to input, just like in any sort of fluid or frankly any solver, you have to input your conditions, geometry, boundary conditions, and then in this case, kind of unique is your molecular interaction model. So here, let's kind of break down how the DSMC algorithm works. First, you have your simulation domain. This is what you're trying to simulate. So in this case here, they were trying to simulate hypersonic flow around over a sphere. So we have our domain. Then we want to, so let's say this is our domain here. We discretize that into all these cells, and we set our boundary conditions. So in this case, our boundary conditions are kind of particles are flowing in here. And then we have probably a pressure vacuum boundary at the top and the bottom, or maybe it's a pressure depending on what the ambient pressure is. So some way to compare the something here to set so you have physical conditions. So you don't want particles just flowing out unrealistically. You don't want them flowing in unrealistically. So something to keep that equilibrium there. And then we populate with our representative particles. So remember, as I said earlier, that you can't track every particle, so DSMC employs these computational particles to represent the real particles. Each computational particle can represent even 10 to the 10 real particles. So this is a very large ratio. So you have, let's say here's all my computational particles, sort of sampled through, set through, and they're all given their position, their velocity, and their internal energies based on those distribution functions. Okay, so now that we set it, we have to go through and actually simulate the flow. So first is that move. So kind of first remember that first term of the Boltzmann equation, particles move, no collisions yet. And then we get to this collide portion, which is the other portion. So we kind of say, oh, they moved. Now what collisions could have happened? Oh, these two particles might have collided. We go through the process. Say they did collide, then they have their new velocity set based on the collision, and they have their different internal energies. And then kind of at the end of the simulation, obviously you want to see what you got. So you post-process, you get your surface properties. So like if you want to measure drag on the sphere, you can sample that on the surface, or if you want to get, in this case, this is probably temperature or something, or pressure. Here, so then you can sample that as well. And the nice thing, by discretizing these with cells, all these properties are taken on a cell-by-cell basis. So this is all, if you make your cell small enough, there's a few benefits to that, but one of them being here, you get a very high resolution for these properties. So you can see we have a very high number of simulated particles. However, number of real particles is much higher than this. So that's why we need these computational particles. And then a key thing for any DSMC model, and we'll go over this a bit, is the physical models. So what happens when two particles collide? You don't want them to just be like, if you have, let's say, complicated molecules, even diatomic, but even, let's say, more complicated molecules colliding, that's, how are all your energies exchanged there? Then the reactions is obviously even a bigger complication on that than if you have such a high energy flow like here. That's a very big factor there. So reactions is a kind of hard thing, but luckily that's been taken care of in many ways for DSMC. And then the surface interaction. So here, obviously, particles are colliding with your sphere. So kind of what goes on there. A nice thing is, remember, this is a purely Monte Carlo approach. We're not solving a differential equation. So let's go through some of the standard DSMC models required for collisions. So one thing, I'm not sure how much of this you went through. You'll certainly go through it more later. And this is a kind of learn about it if you if you use DSMC for your final project. So first is kind of what happens. So when molecules collide, how do they scatter? So what's the deflection angle for the collision? So there's a few common ones. One is Hart sphere. It's very simple mathematically, but it's not realistic at all for because what Hart sphere is just okay. So here's a good picture. So if we assume that this line here is kind of realistic, describes the molecular process. So if when they're far away, they're attracted. Then there's this peak point where they, how far molecules like to be from each other. And then if they get any closer, which was what we required for a collision, there's a high repulsion force. So Hart sphere just means that these are, rigid spheres, set radiuses, and as soon as they touch, the repulsion force is infinite, just for that brief instant. So then some more realistic models used are variable hard sphere and variable soft sphere. I basically kind of make the radius here more variable. So that way they're based on things like velocity. Sorry, I have a bit of a cough. So those try to capture the scattering and eventually diffusion process more carefully, and that's kind of standard used in most DSMC solvers is variable hard sphere and variable soft sphere. Shortly, the one we'll be talking about has both of those in play. So next is collision frequency. So not only do you want to figure out what happens when particles collide, but you need to find out how often do they collide. What's the, per a certain time step, how many collisions do you want to reproduce? Because if you don't get that right, the whole simulation is useless. So there's two common methods here, no time counter, NTC, or modern collision frequency. Professor Alex Nickel will take you through the differences in detail between those two. No time counter is more commonly used, and SPARTA, the code that I'll be sharing with you guys, uses that. The idea is with that is you sample, you basically calculate you have a certain cell, and there you have your particles. So you set your you have a number of collisions you expect there. Then you sample the collisions, calculate if they happened, and with that you'll reproduce your collision frequency, which is your number of collisions you expect per time step. Modern collision frequency works as a different method where basically you have your global time step, and then kind of modern collision frequency you sample this smaller time step, and for every smaller time step you choose a collision, see if it happens, and that ends as soon as the number of your small time steps exceeds your total time step. Next there is the kind of internal energy exchange. Obviously it's very important. Two particles collide. What are their new vibrational, translational, rotational temperatures, or energies rather? And that is done Larsen-Borgnacki method, albeit it's kind of, I believe, the most used in basically every DSMC solver out there. Next is the reaction rates. So this is sort of, obviously when you have two particles, let's say, N2O2, they're colliding, what are your chances of a reaction happening? Because they could all dissociate, they could recombine. If you have just monatomic particles, monatomic atoms in the collision, there could be some recombination. So this is obviously a very important process, very important to your flow. So the most commonly used is the total collision energy. And there's also quantum kinetic, which is, both of these options are offered in SPARTA. The TCE, though, is, I believe, more commonly used. And then kind of the next thing is your gas surface interaction. So here, when a particle collides with your surface, what's going to happen? Is it just reflected? Is it just reflected, kind of like if you think of light being shined on the mirror, or does it scatter diffusely? So specular means that it's as if you shine light off a mirror, and it's reflected perfectly. Diffuse collision means it's scattered. As you can see, this particle collides here, then it can go any way. Kind of the real way is it's a bit of an average between them. So there's kind of so it collides one way and then doesn't collide specularly. That's not realistic because naturally you have to account for things like surface roughness. No surface is completely smooth on the atomic level. So it won't just be a perfect mirror-like collision. It's I believe most surfaces have it's about 90% diffuse, 10% specular. That's kind of a solid assumption in most cases. Certainly for probably the cases you might be running for your project, that will be the case. And then SPARTA or any DSMC solver, it's pretty easy to specify. So next, that I sort of talk to you about all these. You guys feel free to interrupt me if you have any questions. So now I talk to you about all this important things of kind of how does a DSMC solver run. Next is important, so you guys, you won't be setting your DSMC solver, but you want to be using one. So what's important to that? So first thing is you want to define your Knudsen number. So you calculate mean free path. This right here is the equation for a hard sphere. It's kind of for this level, you don't need to be super exact. You just need a solid assumption, and then kind of later when you present your results here, if you publish them in a different environment, as long as you kind of explain how you did it, someone can retrace your steps. But so this is a hard sphere. Mean free path approximation, certainly good enough for this problem setup. And then you choose your characteristic length. In some cases, it might be just like the radius of your body, or if it's, let's say, a nozzle flow, it might be the radius of the throat or something. Some people use diameter, again, as long as you say. I always believe it should be radius. Some people use diameter, some people use kind of whatever they want. As long as you just show what it is, it'll work. Next, you need to select your boundary conditions. In SPARTA, they have all these boundary conditions. So there's the kind of inflow-outflow boundary. So that means particles can freely just flow out of the boundary, but you also let particles flow in. So in the case of that hypersonic flow around a sphere, we have particles flowing in from one of the boundaries. Then there's a pressure boundary, so instead of so you can make it just a complete vacuum, or you can have some sort of basic equilibrium pressure between those boundaries. A surface, so if you want, let's say, one of your boundaries to represent like this table or a substrate, that would be what you want to use. Then reflective boundary means that particles actually collide with your boundary specularly. And that is a good use if you have a symmetric problem. Then, like in the case, if we go back here, so this is a symmetric problem, so we can just simulate half the problem by using this reflective boundary. That would be the same as if we simulate the full problem, only this is only taking half the computational time. So it's good use then. Actually, symmetric, it's like if we have the reflective, but instead of making it just a 2D problem, we want it to be this to be a rotational problem. So going back here, if this was flow over, if we'd made this a reflective boundary, this would be flow over a cylinder. So we assume the cylinder has a span of infinite, and it's a 2D problem that way. If we want to still keep it kind of 3D, we make this axisymmetric, and that way this is a sphere now. So we have flow over a sphere. So depending on what your problem is, And then periodic. Periodic means that if particles are flowing out of one boundary, they flow right in through the opposite boundary. Next, we need to choose the cell size. So, if we go back to this one, each of this, how big should your cells be? First, the kind of DSMC requirement is your cell size should be about your mean free path divided by 3. The reason for that is that because kind of the way with DSMC is when you have particles colliding, there's some random sampling going on. So you choose your first particle, and you choose your second one, and but and it's all within your cell. So if your cell is huge, let's say several mean free paths large, you might be choosing collisions on the opposite side of your cell that there's no way they could happen because their particles are too far apart. So by constraining your cell size to be a fraction of your mean free path, even in the worst case scenario, they're close enough where they could actually collide. And if they're too big, if we go back to this problem, if they're too big, let's say you have a collision here and a collision here. This is totally different flow regimes. At this point, you have a very high density region here, a very low density region here. So particles are colliding much more frequently here than there. So you're violating your conservation of energy at that point. In some cases, though, there might be geometrical constraints. Like if you have some, if my mean free path, especially in low altitude flows, my mean free path could be many meters, even hundreds of meters if you're talking that low density. And your geometry is probably going to be not that big. So you might need to have smaller cells just to capture that. Next is your time step. There's the mean collision time. I believe you guys went over that. That's your average time between collisions. And then called either translational or the residence time step, which is the average time it takes for a particle or molecule to travel through a cell. So you don't want, so in the case of both these time steps, you don't want the collision, you don't want such a big time step that you might be skipping through multiple collisions. So that's why you have your mean collision time divided by 3 to make sure that even kind of worst case scenario, you're still not skipping through collisions. Also, though, on this case of this residence time or translational time, that's how long it takes your particle to move through a cell. So you don't want particle to jump through multiple cells in one time step. Again, that's taking one particle that has a kind of your internal energy profile set in its first location and then moves to a completely different location. So that could be violating your conservation of energy again. So you set sort of these conservative parameters here, and then you pick the smaller time step. And the last thing is defining your number of computational particles. So there's this factor FNUM, which is defined by your number of real particles divided by your number of simulated particles. And so the number of real particles is easy to calculate. You have your number density, you have your volume size, you have your number of real particles. The simulated particles sort of something you want to choose. Usually it's about 20 particles per cell. That's a good kind of starting point. So you calculate, you have my number of cells, I multiply by 20. That's my number simulated. I might get this ratio. I could have my FNUM. Next thing, obviously important to any simulation, is your verification and validation. So in the case of DSMC, verification is, are these numerical procedures and equations I set correctly solved? So make sure that your spatial discretization, how big your cells are, is good. Make sure that this ratio is less than 1. Make sure that I have a good time discretization. Make sure that I have enough particles per cell. If you have too few particles per cell, like if I only have 2 particles per cell, that means these 2 particles are just going to be constantly colliding. And that's, they say that means that their molecular properties aren't random. They're clearly correlated to each other. By having 20, that means that they won't, chances of me having 2 particles collide frequently are very unlikely. So their atomic properties are much more randomly set. And then obviously you need the validation, which is comparing to other numerical, analytical, and experimental results. There's certainly several ways to do this depending on your problem. As you guys go through that, I could certainly talk to you guys individually about,
Just a question about the mesh. Is it like a big problem? Like you spend most of your time doing the mesh, or is it like pretty easy and any mesh kind of works and gives us some answer, but only a good mesh gives like the correct answer? Like convergence problems a lot, or?
That's a great question. So the question, just to repeat for the distance, question is how important is the mesh and how hard is that to set? Like in CFD solvers, certainly the mesh is a very big problem. And then you get all sorts of convergence issues with your mesh. Fortunately, on DSMC, the mesh is much simpler. It's so this is a good example, DSMC simulation over a cow. So in like CFD, this might be a pretty tough problem. You need your good surface mesh, and then you need your boundary layer mesh, and then you need your volume mesh, and it can be very hard. Even the cow has some complicated parts here. DSMC, that's not an issue. You just have your start off with just a uniform mesh, at least in SPARTA. That's the easiest way. And then you could do what's called an adaptive process then that refines and coarsens your mesh based on what's going on. So like if I do it based on number of particles, that means if I have a lot of particles in here, I want to refine that mesh. So in here, that might happen in the stagnation point. In the wake, I might have no particles, so I want to coarsen that mesh. The process is saying the mesh is much simpler. So even if you set a really bad mesh, you'll still get a result. But if you do things like not follow these sort of parameters, the spatial discretization parameters, you'll be violating some fluid properties, but the simulation will still run. You just have to look through the simulation, look through the results to make sure that they're right. Does that answer your question?
Perfect, thanks.
All right.
Yep.
So some popular DSMC codes, there's a lot of them. These are one, Bird is kind of the inventor of DSMC, and you guys will, if you haven't yet, Professor will definitely kind of show you the book, and you should see if I could post it on Piazza. Not sure if I can, but I'll talk to her about it. It's certainly a very good reference. There's some basic equation stuff in there, and if you really want to dig into DSMC, he's obviously the inventor, so he explains the method very well. It's kind of simple. All his codes are written in Fortran. They're just serial processes. So this is a good way if you want to learn DSMC is to really dig into his code. The one we'll be using is SPARTA down here. This is developed by Dr. Gallus and Dr. Plimpton at Sandia. This is it's open source, and unlike a lot of other open source codes, this has a very good documentation. So the manual is several hundred pages long, explaining every feature there. So it's it's a really good documentation, and I'll try kind of walking you through this, how to set up SPARTA, how to run some of the basic things, and hopefully that'll be good for you guys to do your projects. So now that we went through all the theory, let's kind of walk through some examples. It's still have a bit over 20 minutes, so that's good. So in SPARTA, they have a few examples here. So this is a instability flow where they have, I believe it was argon on top and like helium on the bottom or something, and they just have gravity here. So eventually, kind of with your denser gas, that'll be pulling with gravity, that'll be pulling your denser gas down. And you kind of see this instability form. This was, I believe, their kind of first case where they showcased SPARTA and showed what it can do. And these sort of instability flows have been in the past tough for DSMC to do. So they're trying to that's a big part of their work, is showing that SPARTA can handle these. Next is kind of flow around the space station. And then they show heat. They're showing heat flux on the space station and the kind of flow around it. One thing that they released is nice is, see if I can restart these. So they kind of released these images where you can see the particles move. So you can't get any quantitative results here, but you can sort of see, does it look right? Do you have particles flowing from the right way? Things like that. In this case, this is one of the adaptive meshes. Here, you can see the mesh is constantly changing. But here the geometry is also moving, so this becomes a much harder problem to solve. Certainly there's frankly no good way to solve such a problem in DSMC, because if you think about it, so this is moving. What happens to the particles that are in the area where this geometry is about to move into? I I believe, last I heard of this, their solution was just to take those out because they didn't know what to do with them. That's not very realistic though, because those particles, if you think of the particles here, now this one is just hitting it, so it actually has a pretty high velocity. So by taking it out, or if you're just moving the particle out of the way, you're not reflecting that appropriately. So it's but I know what they should do. Like, it is a very tough problem to solve in this. One case that I worked on a lot is working on this vacuum sensor. It's called the Micro. Some people in Professor Alexeiko's group I came up with this sensor, and I did a lot of the DSMC simulations. And one nice thing with DSMC is you can simulate these low pressure environments and microscale MEMS-based sensors. Now you can see how small this sensor is here. So kind of going through, and this is a lot of the setup that I was talking about. So our collision models, a no time counter, that's a model used to set the collision frequency, variable heart sphere, and Larsen-Borgnacki for your internal energy exchange. We ended up having about 10 to the 7 computational particles. Our time step was 1 nanosecond. Turned out we needed a very small time step for this. And our spatial discretization was 300 by 150 collision cells. Though this gap was kind of key to us, so we wanted at least 5 cells between that gap, so that was sort of our constraint here. And you can see all of our flow conditions. We had our pressures, our Knudsen numbers, and the temperature of the beams. And that's a infrared image of when the when the sensor was on. You can see that this kind of lit up, and you see the heater beam. That's this here. So that was a hot beam, and we had this cold beam. It's not as easy to see, but it's there. And you can see the flow field structure. It's a very complicated structure. So we had, in this case, all of our different cases. We had the different temperatures of the beam set. There was no ambient velocity here, but you can see that the velocity could peak at like almost a meter per second, which isn't very high, but kind of given that was a microscale and there was no ambient velocity, it's certainly surprising that such a velocity could form from nothing, so to speak. So that was due to these high temperature regions, because you think here, the difference in temperatures here is 64 degrees, right? This is a 20 micron gap. So that ends up being a very large temperature gradient. That's over 1,000,000 degrees per meter. So that's a very high temperature gradient. And that creates these sort of very interesting flow fields here. And this was a complex case because of all these vortices forming and everything. We actually had to go with a lot more particles per cell. So some points, like when I say 20 particles per cell, you run that, you start that off, you see how it works. This case, though, we were seeing that some of our sampling and things onto vortices, they didn't look so good. So we ended up increasing, I believe, to 100 particles per cell. And that's when we start getting that resolution that we wanted there. And ultimately, this is us going through the validation process. So basically, this was the experimental results. And we basically simulated the 2 extreme cases here of the hot pair and the colder pair. We see that we kind of, we sandwiched the experimental results nicely. So this was our validation, showing that we did this, and we got some good results here. Another case is the CubeSat reentry flow. So this right here is kind of a common case in reentry, but it's very non-intuitive. So when you have kind of in the continuum world, when you think of supersonic or hypersonic object, you have this shock form, and it's a very fine line, right? In CFD, it's actually modeled as a discontinuity because you have such a rapid change of properties over this very small period, small length scale. In rarefied flow, though, because you get free molecular, as this turns out, this is in the low Earth orbit, so this is a very low pressure. So the shock here is actually very diffuse. Here our CubeSat is 30 centimeters long. The shock looks like it's probably longer than that. So it's not this finite line, it's a pretty diffuse shock. So this is common in rarefied flow because you don't have enough particles to collide. So kind of when particles are reflected off your front surface of the CubeSat, they're traveling for quite a while before they collide with particles from the free stream, if that makes sense. Also, look at this here. This slice here is showing your temperature. You can see it peaks there at over 20,000 degrees. That should scare some people. But that's also a common effect of this sort of flows where you reach, this is where it gets non-equilibrium. So we don't have enough collisions to equilibrate our flow. So all of our particles are, so if we go back, sorry, let me take a step back. So we have our translational temperature, which is just defined based on your your molecular motion with respect to other molecules. So if I take a snapshot right here, look at my how fast my particles are moving with respect to each other. Based on that, I can get a temperature. That's just a definition of temperature. So here I have molecules that are traveling at 8 kilometers per second one way, and they are reflected off the CubeSat and bounce off the other. So that's a very large velocity discrepancy. Like there's a very large change there because you have 8 kilometers per second one way and some other velocity going the other way. So let's say, even if it's 0, that still is a very big difference. So that creates this 20,000 degree temperature here. You can see this is the speed flow field here, and so it goes down. This kind of behaves naturally, just over a much slower scale. So naturally in continuous flow and behind the shock, you have very low speeds, and in stagnation point, obviously your velocity is 0. So that's what we're having here. Just our shock is very diffuse. Another case we studied for the same project was these pressure settling chambers. Basically, this was a very big design project. And the thing here was just, see, we're looking at we had to meet some sensor requirements here, very specific, as well as the overall CubeSat requirements. Basically, what we needed here is we needed a flow environment that was controlled in terms of temperature, and also we need to make sure that our environment was steady, so things weren't changing a lot in there. So we came up with these sort of settling chambers where particles would fly in, they'd collide with the back wall, and they'd diffuse within this settling chamber. So their temperature would be equal to the back wall, or about. The velocity would be pretty low because that it's about 0 in here. It's 8 kilometers per second out here, but within here, after it collides, it's about 0. And kind of things don't change super rapidly in these settling chambers. So that way we're able to get a very good pressure reading in here. All right, so it looks like I still have some time to go over SPARTA specifically. This will just be through slides. I'll try to make sure, but I should be able to post these slides on Piazza so you can reference these. And at some point later, I'll try to pull up my laptop or something and kind of actually walk through the process with you. So you use SPARTA. You can go to this page, sparta.sandia.gov. Download it. It's open source. You have documentation, tutorials, things like that.
Do you use Fortran?
This is using C++. Yeah, nice thing with SPARTA, I should say, is it's was one of the people, Dr. Plipta, is actually a computer science person, so he is a very good C++ coder. He made it very efficient. It's very parallelizable, has very high performance. Everything about that's good. If you don't know much about C++, you have to dig into the code. It's a bit of a pain. That's what I've had to do. But hopefully you guys don't have to do that. Nice thing is there's a manual, but also through this online feature, you can get the specific command list that you want. It kind of walks you through all the commands, has a nice long explanation. Ultimately, go to download. You download it. Pretty simple. One thing I should mention here, move it to the end. I want to make sure I get to it. So you need some sort of Unix environment to run this. And we'll be running on the clusters. Don't know if you know, but Purdue has a very nice cluster supercomputer, quite a few of them, and they're all run called clusters. So you have to we'll get an account set up. I'm not exactly sure how that'll work, but we will get some access for this class available. And then then what you have to do is, if you're running SPARTA for this, is you need some kind of Unix platform. So one option is the secure FXCRT. So you go to this website, you get it, then you go through the process of how to of installing it and then uploading SPARTA there. And all these slides will be available so you can go through that process, or anything else will work. If you have Linux or Mac, it's simple. If you have Windows, well, there's also other options out there. See how many of these I can get through. So SPARTA has a few sample cases available for you as well. So one of them is the rotating flow around an ellipse. If you remember that there was that moving ellipse earlier, that's what this is. So this is what the first half of the input script looks like of SPARTA. So you set up, so here dimension problem, do you want a 2D or 3D problem? Those are your only options. If you want a 1D problem or a 0D problem, you make it 2D and then you set the boundary conditions such that it acts like a 1D or 0D problem. The boundary conditions here. So O is outflow, R is reflective or specular, P is periodic, there's also S for surface, and there's A for axisymmetric. I create my box, so this is my simulation domain. In this case, this is a 2D, so the third dimension. You have to specify a third dimension, but you just set it negative 0.5 to 0.5. Then, in this case, this is 0 to 10 meters. Create my grid, 10. So there's 10 cells in the X, 10 cells in the Y. Because it's 2D, you just have one in the Z. This is a very coarse mesh, so you definitely will not be using this coarse of a mesh. Here, number density. So in this case, this is again just 1, so 1 particle per cubic meter. Then FNUM, that's what we were going over earlier. Then you set the species. So in this case, they're using nitrogen and oxygen. There's a few more options they have available, and also if you need to include your own species, you can add them easily. I'll show you how to do that later through a different lecture. And then your mixture, so you set, okay, so I want both of these molecules and they'll be moving at a velocity of 100 meters per second in the x direction. So my surface, in this case, I have this circular ellipse that I read in, and then if needed, based on the file, if that's let's say how you want it, you can change its origin and scale it as appropriate. So they have a circle and then they scale it to make it an ellipse here. So now here's where you define how your particles are colliding with your surface. So I want them, in this case, this is saying I want them to be completely diffuse. So 1 means kind of how much of a, so 1, this means 100% diffuse. If I add 0.5, this would be 50% diffuse collisions. And then 300 means that's a temperature. Sorry, I made a mistake. 1 is something else. This is the surface collision ID. Diffuse means they want diffuse collisions. 300 is temperature, and 0, this is the accommodation coefficient. So this means actually 0% of collisions are diffuse. So this is the way they set up here, these are all specular collisions. If you had 1.0, that would be diffuse. And if you had 0.9, which is usually what you'd go with, that would be 90% of collisions are diffuse, 10% are specular. That's the way DSMC handles that. Collide, in this file, air.vss, you have your collision, you have your VSS or VHS collision coefficient, collision parameters. So this is just saying, oh, I want my nitrogen and oxygen atoms to collide according to what's specified in this file. Here, this is telling SPARTA that they are emitting particles from the lower X boundary. So if you don't specify this, that means that no particles will be flowing in. So this is important. And then time step is specified. All right. So these are some of the commands, and these you really want to, at this point, once you know you want to do that, you look through the manual to really see exactly what you want. The idea here is this is dumping those images. If you remember, that's there are the GIFs shown here. So here down, you can get those images. That way you can kind of see the particles moving around and things like that. Yeah, and in this case, this is how they're rotating here. Actually, not super familiar. I've never had to move a surface in SPARTA, but this, I guess, is the command to do it.
Sorry.
Oh, yeah.
The number density that you were talking about in the last slide.
Yeah, this is a very low number density.
Yeah. Is that like the representative particles or the actual particles?
So this is real number density.
Okay.
So actually, you'd have something much higher. You'd have like, if you want to simulate atmospheric flow, it'd be 10 to the 25
Right.
or something. So it looks like here they have an F-num being low here, less than 1. So if it's 1, that means you have 1 computational particle per real particle. So in this case, it looks like they have 1,000 computational particles for 1 real particle. So it's a very weird case that they set up here. Basically, so you run this, and then you get here's a bunch of outputs here. So this is a kind of nice thing. This is you can look to make sure your case is running and looks good. So this is your step number, your time. Well, here's a good thing. So NP is number of particles. So you want to make sure your flow reaches steady state, which you can do once this number of particles steadies out. In this case, you can see it's still increasing. So it's not steady yet. Then NATT, that's number of attempted collisions, 0. So the number of collisions is 0. But because the number density is so low, the mean free path is so high, the particles aren't going to collide with themselves. But we have a bunch of surface collisions happening here. And once you convert all your image files into a GIF, you get this sort of image. And with this sort of thing, so let's say that you're trying to actually get some results from here. This is kind of a good way to run a very quick case. We have a very unrealistic number density here. But this is a quick case that you're sort of making sure, oh, look, my boundary conditions are right. It's generally doing what I want it to do. Now I can run a longer, more realistic case. So that's kind of the point of this. Next is, all right, so this is, I won't have time to go through this, but this is just flow around a cylinder. I'll just go over this slide here. So in this case, I have my geometry specified. This is a symmetry plane, so this is a 2D case. If I want an axisymmetric, if I want a 3D case, the simplest would be to make this an axisymmetric plane, so it's flow over a sphere. In this case, they just have particles flowing in through this boundary here. And these two are specified as vacuum boundary conditions, so kind of pressure boundaries with a back pressure of 0. You can also specify the pressure boundary with the back pressure of what the ambient pressure is. So in this case, number density 10 to the 20. I have my temperature and my velocity here. So the first thing done here is you try to kind of get your mean free path. Just compute it through with the hard sphere approximation here. My Knudsen number, so my length scale in this case will just be the radius. And then calculate the number of cells required in the x and y direction. And then calculate time step. And here, their input file is given here. Some of these cases, their syntax updated from the versions, but not all of their example files actually, the files they gave you actually have those updates appropriate. So you might have to, hopefully I'll be able to give you the sample scripts that are updated. That will be my goal. This sort of shows you using, this case, this is using the secure CRT, secure FX CRT. That's Israel who put this together. That's what he used. So this is, if you want to go that path, you could. This shows you how to do that. Then you run. Here we see image of the particles flowing over the circle. And here you can see, okay, so the particles are flowing the right way. They're not all flowing out of the boundary, so that's good. Oh, and look, I have some collisions happening here, something going on, so that's nice. No particles are flowing inside of the circle, that's also good. And, okay, so you see this image, and it's looking pretty good. This shows you how to use TechPlot, which is a post-processing software available to all of us, because we're all Purdue students. At some point, different lecture, I'll show you how to do this. Looks like we're out of time.